Okay, so regression analysis, basically it's referred to as curve fitting, or if you have only two variables. But in curve fitting, I'll show you how regression works, and it's basically an example that I have used from our software. If you look at it, I have certain points here. I have 1, 2, 3, 4, 5. Can you see the 5 points on the graph here? Right. So these are the 5 points, and we fit a line through these points. Right. What regression analysis does is it takes the data and it tries to fit the line through it so that the distance between every point and the line is such that it minimizes that distance. Right? That's what we call as the sum of squared residuals. A few things that of interest. On the top here, you see r squared as 0.19. Okay, here. I'll explain what r squared is. Simply, it's a statistic. It's a statistic that varies between 0 and 1. 1 being a good fit and 0 being a poor fit. But if you look at 0.19, I would say that the model is explaining 19% of the variance in the underlying data. Okay, and our goal is to explain as much variance as we possibly can in the underlying data. Now, if you just look at this data, and there's a scatter and there's a line going through it, what I did is I added more points. Okay, same thing, I added more points, and now you see that the line is fitting a little better. I did not remove the other points. Those 4 or 5 points are still here. I have not changed it, but look, the model fit here moves up to 0.66. So now, based on this data set, the line is fitting more closely. We are explaining 66% variance in our underlying data set. Right? Okay. Then I just add one outlier, right? Just 1 point. Compare this to this. Nothing else changes. I just add one more point here. And the slope of the line changes. And look, from 66% fit, we go down to 23%. Right? So this is what, in general, happening in a regression analysis. We're trying to fit a line to a scatter plot that we have. And this is a relationship between two variables. Imagine if you have more than two variables, and this become a little daunting task. You cannot just visually fit lines to it. You need some mathematics, some calculus behind it. So here's our first example of regression analysis. Right? What I have here is the relationship between weight and height for women. Right? Some data that I got my hands on. And if you look at the graph on the other side here, you'll see that I have plotted height in inches from 58 inches to 72 inches and weight in pounds, right? And I have the relationship graphed, right? Now, the data set gives us the average height and weight for American women between the ages of 30 and 39. And first thing I did, I summarized the two variables in the data set, right? So the minimum height is 58 inches, and the mean height is 65 inches, maximum height is 72 inches. The minimum weight is 115, maximum is 164 pounds, and the average mean weight is 136 pounds, right? The question I'm interested in answering is how much weight increases for a given increase in height, right? If the height increases by 1 inch, right, how much would it increase? How much weight would increase as a result of that increase in height? Right? So for this, you run a regression model. And first step, I write my model that weight is equal to f of height, which is weight is a function of height. That's my hypothesis, right? So the regression model gives me weight is equal to constant plus a coefficient, which we call beta 1 times height. Right? So after you run the model, you have the constant here, which is minus 87.5, and the height here, which is 3.45. Now notice that I have 4 boxes highlighted in green. Right? The first box is the estimate or the coefficient. Regardless of what software you use, you'll get the same thing, right? Coefficients, and then you get the standard error of the coefficient. And if you divide this with the standard error, you obtain the t-value, right? The t-statistic. That was the answer. Anytime you divide the estimate with standard error, you get a t-stat. And that is what is reported in almost every statistical software. Now, this is minus 14. If you have a negative coefficient, you have a negative t-value. And then I have here 3 stars next to this, and the probability, which is very little, 1.71 raised to the power minus 9, and here raised to the power minus 14, so almost 0. The number I'm looking for here is 0.05, right? If it's any less than 0.05, I'm happy. And this star just tells me that this coefficient is statistically significant at a very high level, 99.99%. Okay? And look at the R squared. It's 0.99. This model is explaining 99% variance in weight using height as an explanatory variable. Right? Now, let's look at t-value. What is t-value? The coefficient is minus 87.5, and the height coefficient is 3.45. Anytime you get a t-value that is greater than 1.96 in absolute terms, okay? 1.96 in absolute terms, then it's a statistically significant coefficient. It means that this coefficient is statistically different from 0, and hence it has some theoretical or some statistical value to it. Okay? Anytime you get a t-stat of less than 1.96, and assuming that you are only interested in 95% threshold, then you cannot say that you can reject the null hypothesis. And the null hypothesis is that this coefficient is 0, which means that there is no relationship between the explanatory and the dependent variable. Right? So the t-stat allows you to say, no, sir, there is a statistical relationship between the explanatory variable and the dependent variable. In our case here, the explanatory variable is height. The dependent variable is weight. We are explaining differences or evolution or change in weight as a function of height. Right? So the intercept is minus 14.7. Usually we do not look at the t-stat for the intercept or the constant because it's not an explanatory variable. It's just a conditional mean. What we are interested in is the coefficient for height, and the coefficient for height is 3.45. The t-value is 37.8, so I can say that I can reject the null hypothesis that this height coefficient is 0. Right? And then what is the height coefficient? It's 3.45. What does it mean? That for a given increase, for a unit increase in height, and in our case the unit is inches, so for 1 inch increase in height, the weight goes up by 3.45 pounds. Right? The dependent variable and the explanatory variables, whatever units you have them in, the model explains them in exactly the same units. Right? So for every increase, for a unit increase in height, for every inch increase in height, the weight increases by 3.45 or 3.5 pounds. And it's a good model. And how do we write it in an equation format? Weight is equal to minus 87.5 plus 3.45 times height. Now, conceptually, a negative weight means nothing, right? What is minus 87.5 pounds? I mean, you can have the thinnest model possible, but she or he would not have negative weight, right? At the end of the day, everyone has positive weight. Right? So what is happening is, because since we do not have anyone with the height 0, right? Only then this negative weight is of significance if you have height as 0. But the minimum height in our data set is what? I'll just scroll back. Minimum height is 58 inches. So what is 3.45 times 58? So if you substitute 3.45 times 58, you add the back, and that would give you the mean value for the weight. And if you keep on